All right. So when you think about mainframes, the words that might typically come to mind are legacy, old, expensive, outdated, complicated. But you most likely wouldn't really think about them in a cloud native context. And hopefully, with my talk today, I can convince you that mainframes are indeed still relevant and they have their place in the cloud native world. And before we get into it too deep, I want to give a quick shout out to the whole project team behind it, and especially one of my colleagues, Yannick here, who is all the way on the right and is working with me on the Kubernetes on mainframe part of the project. He's really good at rubber ducking and asking the right questions. And speaking of questions, these are the questions I want to answer here today. So first of all, I'd like to establish a little bit of a common understanding of what mainframes really are, because if I look at the audience, we're not all in the mainframe age. So neither am I, to be fair. But yeah, and then we'll look at if they still actually matter, how they work, why you would want to put containers on them in the first place. And then finally, the technical aspect, how do you actually put containers on them? So let's get right into it. First question, aren't mainframes legacy infrastructure? Yes, but also no. I'll explain. So yes, they're legacy because they've been around since the 50s. They still run COBOL. They're often tied to these old school institutions like banks, governments, insurance companies, or telcos. And a lot of their workloads were written decades ago, and they're still running completely untouched, unmodified. And they're not trendy at all. They don't fit the modern move fast and break things mentality. But also no, because they're still evolving. There are modern mainframes that are still being developed and are coming out, and they run Linux. They support cloud integration. They even have AI accelerators, so maybe they are a little bit more trendy again now soon. And they still process absurd amounts of data with higher efficiency and reliability than huge racks of x86 servers. And the companies that rely on this kind of crazy security and raw transaction powers still buy new mainframes to this day. So they're not going away. They're just kind of invisible because they just work and aren't as hyped as some other technologies. But aren't they just big, expensive servers? Not exactly, kind of. Well, they're like the computing equivalent of a nuclear bunker. So they're they're ultra reliable, high throughput, and disaster-proof computers. So why was I getting into the whole mainframe topic? Because it's not like a typical project for me as well. I found out that IBM tests all of their components against things like earthquakes and radiation. And when they test for that, it's not just like some guy shaking the rack. It's like an actual earthquake simulator, and they do it under load, and the workload has to like keep running. And yeah, they also have crazy things like redundant battery backups, self-contained redundant water cooling systems. Yeah, they're actually, IBM mainframes were the first enterprise appliance back in the day that supported water cooling in the first place. And the joke was that if you have problems with your mainframe, you have to call a plumber and not an engineer. So, and yeah, their hardware, firmware, and OS are really fine-tuned to work with each other and built for these mission-critical workloads. So the kind that are impractical to handle on regular distributed systems. And the most common examples for that would be maybe withdrawing money from an ATM where you don't want to wait like 30 seconds or so for your balance to show up, for your money to come out. Yeah, or also credit card transactions where you just handle just millions of them in a really short amount of time. And to put that into numbers, actually 90% of all credit card transactions are still handled by mainframes. and about 70% of all Fortune 500 companies still use them, and almost 70% of all production workloads just globally run on them, while just accounting for 6% of the costs. Okay, so I hope we have a basic common understanding that mainframes still matter at least somewhat. Now let's see how they work and what actually makes them special. So as I mentioned, on the hardware level, all the components are really fine-tuned to work with each other, and all that with super low latency because it's all in the same machine. And I'm sure some of you have built your own computers before, or taken apart one at least. So your regular run-of-the-mill consumer CPU maybe fits in the palm of your hand, right? These mainframe CPUs are usually bigger than your hand, and there's a lot of crazy computing power in them. And you can do things like hot swap them while the mainframe is running, and it doesn't affect it, doesn't care. And I think the SLA they built these mainframes for is 7 nines, so that's a 3-second downtime per year. So crazy reliability. And another special thing about hardware that we'll touch on later is crypto modules that they have on board. So it's kind of like an onboard HSM to handle encryption and other stuff like that. And I'll cut things short here because you could do a whole lecture just on what makes the hardware really special. Yeah. And on the systems level, the key takeaway you can take away from this big slide here is really that you can run all kinds of different workloads on them, either natively on the mainframe itself or virtualized in some way. And depending on the hypervisor technology, you can do it with practically zero overhead at all. So on this diagram here, for example, we can see some KVM stuff. We can see ZVM, which is like the IBM technology for virtual machines on there. And we also have LPARs. And LPAR is short for logical partition. And it's basically a slice of compute of the mainframe, and for simplicity's sake, it kind of behaves like a VM, but it's closer to the bare metal itself. So the mainframe has a type 1 hypervisor baked into the firmware, and each LPAR gets direct access to a slice of CPU, memory, and I/O, and it's not time sliced like a typical VM. Right. So why would you put containers on them? So we have a basic understanding of how the mainframes work. And since this is KCD, we'll get into the actual container part now. Why would you want to run containers on a mainframe? So there are several points to that. So you can modernize legacy apps more easily, so running microservices alongside old school COBOL without breaking things. Security and isolation is the use case I'll get into a little bit more later. So the built-in encryption stuff, having better isolation than typical cloud infrastructure. Low latency itself, so running these containers next to mainframe databases also equals faster transactions. And the whole cloud sovereignty discussion, they're becoming more interesting again to have cloud-like agility without leaving your data center. And also cost savings are a factor in the end, because depending on your workload, running them on a mainframe can be cheaper than using the cloud or having racks of x86 servers. So the specific use case I'm working on is using confidential containers. So using OpenShift sandbox containers, which is basically the downstream product of Kata containers that you've probably heard of. And for those that haven't, Kata containers are basically containers that run inside a confidential virtual machine. So using the hardware-backed trusted execution environments that come as part of the CPU. And why is that even necessary? So most normal containers aren't really isolated. They share the kernel and they trust the host. And Kata kind of fixes that by running each container inside a lightweight VM. And if you add in the confidential computing tech, now you have confidential containers. And your app runs in the VM and the host can't peek into it. And even if the host is compromised, then your workload is still secure. There are three core components really to Kata. So on one hand, you have the confidential computing part, which is the CPU level features to encrypt memory and block host access. You have the attestation engine to verify the workload owner and that the container is running in the trusted environment before starting any sensitive operations. And then you have encrypted image pools and the file system. So the images themselves and secrets can be encrypted and decrypted inside the trusted environment only, and the host can't read them. Now, for my use case, I'm using this IBM HyperProtect secure enclave, which uses for the Kata attestation service. And that is based on these Linux One secure enclaves. So it has hardware-based isolation and uses the firmware crypto modules. And yeah, in normal Kata deployments, your trust anchor would have to be something external, like a different cloud or a different data center. And with this approach, we can contain everything in one system. So how do you put containers on mainframe? Like most things, it's a typical consultant answer. It depends. Like there are many ways of doing it. Technically, you can even run containers natively on z/OS with container extensions. I actually found that out a couple of weeks ago, which is really fascinating reading documentation that it uses Docker Swarm under the hood. It's just kind of strange to me. But we're at KCD, so I'll tell you two ways that I've used to put Kubernetes on the mainframe. Before we do that, we have to take one quick detour. So a big differentiator on the software side of things and a bit of an initial hurdle is the systems architecture. So similarly how a lot of things didn't work, or to some extent still don't work on Apple Silicon, we have a different system architecture on mainframe, which is this S390X. And the first draft of this slide was just like a table side-by-side comparison of the different features and what differentiates them. And I thought that's really boring. I don't think anyone will pay attention to that. So I'm trying to explain it with an animal analogy. So I want you to think of S390 kind of as the octopus, because it has insane parallelism, kind of like all the tentacles can act in an independent but coordinated way, and they're crazy multitaskers. And also you have fault tolerance. So I don't know if you knew this, if an octopus loses a tentacle, it can actually grow it back. And on the other side is a domesticated raccoon. It can do a lot of things, but not always in the cleanest way possible. And it's a little less efficient, so it might try doing 10 things at once, but it might end up breaking something. And yeah, panic under load. And also if you cut off a finger, then you have to go to the vet. It doesn't fix itself. All right, so the first scenario of putting Kubernetes on the mainframe here and to show you is we have the control plane and one worker on a regular x86 cluster, and we want to join a worker on ZVM, and it's just vanilla Kubernetes. It's easy, right? After all, it's just another Linux machine, you install some packages on it, you enable some systemd units, and you join it to the cluster. Yes, actually it's surprisingly easy. So yeah, this example is just regular vanilla Kubernetes on Ubuntu bare metal hosts and Ubuntu ZVM. And the only real challenges to do this were deploying the CNI to be multi-arch and adding some labels to the node so the workloads go to the right node. And yeah, here we can see a workload running on the S390X arch as well. Now, the second scenario is another way I've done this, but the key differentiator here is that it's an OpenShift cluster and it's an LPAR instead of ZVM. It's easy, right? No, so unfortunately not. There are two fundamental differences and they're related to each other. So first of all, OpenShift uses CoreOS, which is Red Hat Enterprise Linux, but super optimized to run Kubernetes, and it's immutable. And the second reason is LPARs hate me. And by hate, I mean they're very particular about how they work and how they will boot or not boot an operating system. And I'll show you how that works. So if we just try booting an LPAR with a regular off-the-rack CoreOS ISO, nothing happens. So to boot, we need two files. We have an instructions file, which specifies the kernel, the init RAM disk, a parameters file, and some memory load addresses. And the parameters file just contains kernel boot parameters. Some of the parameters I can call out, for example, are the ignition. If you've worked with OpenShift, probably heard of that. So this partitions the drive, sets up networking, and some of the other initial stuff that you need to join the cluster. By the way, the parameters file, this right here actually wouldn't work because it has to be just one line. And I learned that the hard way because I looked at the LPAR and then I was surprised that it would only like set the first line every time. Yeah, it has to be one line. And then also there is a bug in the CoreOS ISO. I wonder if someone can spot it. I'm making sure you're paying attention. Can someone spot the bug? Yeah? Yeah. Yeah, I meant something different. Okay, I'll reveal it. Yeah, the path is actually incorrect. So it's referencing images and it's actually an images pixie boot. And it has been that way since 2020. And no one noticed because according to engineering, it only affects CoreOS on LPAR. And apparently I was the first one to ever try doing that. But they fixed it last week. So the same day I reported it. Okay, once we have a working ISO, how do we even get it into the mainframe? The recommended way to do it is using SFTP, so secure FTP. But of course, we had networking issues, so we couldn't do that either. And the way I did it then was create a custom ISO, upload it to the hardware management console. And I had to do that over and over again over a VPN connection, which took quite a while. And yeah, you can't move fast and break things that easily with a mainframe. It was pretty painful. Yeah, but once that is overcome, this is kind of the setup you need to make it boot, actually. So yeah, ideally you have an SFTP server. And then you serve the ignition file from the existing server, from the existing cluster. They have an endpoint. And what is special here as well is that we're not installing the operating system into DASD, which is the onboard storage of the mainframe, but to an IBM Fiber Channel storage system. This is another thing that complicates things. But diagrams can get a little bit abstract. I'll show you what this looks like in real life. So this is the mainframe from behind and the storage system. Put the boxes here. So the top drawer, in mainframe terms, you call it like drawers, is the HMC or hardware management console that we connect to. And then that is the back of the fiber channel storage that has like these fiber connections going to the mainframe. And then to the right of that is the rack of x86 servers. I didn't get them in the picture. You just have to believe me that they're actually there. Yeah, once we've overcome that hurdle, then we can observe the install process from this beautiful console. And then after the initial install, we change the boot disk from ISO to SAN, reboot it. And we have mainframe. We have, with those hurdles overcome, we can deploy workloads to our mainframe worker. Things aren't quite as hard if you're not the first person to ever do it, but yeah. And yeah, this is the worker with the architecture label. Yay. So to kind of wrap things up, we covered so far. So we have established what mainframes are. Hopefully we've established that they still matter. Went into how they work, why you would put containers on them, and explored some ways to put containers on them with the hurdles. So what's next? So maybe this talk got some of you interested in learning a little bit more. So I've collected a couple of links for you with some good resources if you want to learn more about modern mainframes and confidential computing. So the Open Mainframe project is an initiative by the Linux Foundation, kind of like the CNCF. And one of their initiatives is Ambitus, which focuses on porting open source software to mainframe architecture. There's the Linux One Community Cloud, because of course not everyone has a mainframe at home to play around with. You can get a ZVM, yeah. And I think it's free for half a year. And if you run an open source project, then you can apply to have like a permanent ZVM. And then finally, if you want to learn more about OpenShift sandbox containers, there's also a Red Hat page on that I've linked for you. And that's me next to the mainframe.